Last time we saw that if you have a matrix A over a field, an m by n matrix with entries in a field F, then A is equivalent to a unique matrix of the form 1 1 1 0 0 0. And this number of ones here is the rank of A. And I gave you an algorithm for doing this. Basically, you reduce A to a matrix with non-zero entries on the diagonal, and then you can scale those diagonal entries to be 1 and zeros everywhere else. Now this time we are going to see what happens if we change this field F to a ring R. Well, let's say a commutative ring. But to start with, let's see what happens when we take a Euclidean domain. Later we will replace it by a slightly more general case of what happens when you take R to be a principal ideal domain. In that case, the canonical form is not so simple. It's not just determined by an integer R, which is the rank. It's a bit more complicated. And this canonical form is called the Smith canonical form. So this lecture is called Smith canonical form, or sometimes called Smith normal form. So what it says is that instead of a bunch of ones, you will have entries d1, d2, dr along the diagonal, such that the ideal of d1, or maybe I'll just write it in terms of divisibility, d1 divides d2 divides d3 all the way up to divides dr. Or in other words, we can say that the ideal of d1 contains the ideal of d2 contains the ideal of dr. And moreover, this is not exactly unique. It's only that these ideals are unique. So this form is unique up to the choice of ideals generated by d1, d2, dr. So let me state it more formally. Theorem: let R be a Euclidean domain then every matrix A with entries in R is equivalent to a matrix of the form d1 dr 0 0 for some r less than or equal to minimum of m and n, in fact, where the ideal generated by d1 contains the ideal generated by d2 contains the ideal generated by dr, and this form is unique up to multiplying these entries d1, d2, dr by units. So these ideals are uniquely determined by A. And so I'll prove this in two parts. Firstly, I'll show that you can start with any matrix of a Euclidean domain and then reduce it to a Smith canonical form. And then I'll show that this Smith canonical form is essentially unique. The first part will proceed as in the last lecture. I'll give you an algorithm. Okay, so before we begin to study this algorithm, let's just recall what a Euclidean domain is. So recall that a Euclidean domain R comes with a size function and this function, which we usually denote by d, goes from R to the set, let's say non-negative integers, and it has the property that for all mn in R, if m is not 0, there exist q and r in R such that n is equal to qm plus r, and dr is strictly less than dm, or r is equal to 0. So either m divides n, or you can subtract a multiple of m from n to get a remainder whose size is strictly smaller than the size of m. And an important feature here is that the values that the size function can take are non-negative integers. So if you have some sort of algorithm where at each step you strictly decrease the size, then that algorithm has to stop after a finite number of steps. And that is something that we are going to take advantage of time and again in today's lecture. So let me give you the proof of Smith canonical form. So it's really an algorithm. So the algorithm will proceed by an induction step. So the main loop of the algorithm, so to speak, is an induction step. So the induction step says that A is similar to a matrix of the form D1 0 0 0 here in the first row, 0 0 in the first column, except for this first entry, and then another matrix A prime where D1 divides all the entries of A prime. Once we do this induction step, we can repeat it on the submatrix A prime, and when we do row and column operations only on the submatrix A prime, it will not affect the first row of A or the first column of A. And so we can proceed inductively till this matrix that we get, the smaller submatrix, becomes 0, or the matrix A itself is exhausted, and we will definitely end up with a Smith canonical form. So firstly, okay, so here's the algorithm. If A is 0, then you're done, right? Do nothing. Okay, but otherwise, by interchanging rows and columns, can assume that A11 is not equal to 0, because there will be some non-zero entry somewhere in A. You just, by interchanging rows, you move it up to the first row, and then by interchanging columns, you move it to the 1/1 place. Now what I want to do is try to clear off the remaining entries of the first column. Now, if A1j is not equal to 0 for some j, then one of two things can happen. Either A1j equals QA11 plus R, where R is equal to 0, or the other thing that can happen is dr is less than dA11. Okay, so now if R is equal to 0, so what we have is Q A1j equals QA11, right? That's what we are saying. So then what we can do is, so we have this A11 here, we have a bunch of stuff here, and we have A1j here, and so this is our matrix, and we have some stuff here. I don't really care. So if R equals 0, what you do is you perform the column operation. Cj goes to Cj minus QC1. So what will happen is that we will take this entry and subtract Q times A11 from it, and so this will now become 0. And so we will get A1j becomes 0. If R is not 0, then you still do the same operation. You do Cj goes to Cj minus QC1. And now, instead of 0, you get R here. And then what you do is you interchange the jth column and the first column. So now what happens is that this R comes over here and the A11 comes over here. So what we have is that at this point we have reduced the value of VA11. So this is R is the new A11. So every time there's a non-zero element in the first row of A beyond this, except for the first column, what we can do is we can either kill it or we can reduce the D. We can reduce the size of the 1/1 entry of A by performing 2 column operations. So this process of reducing the size of DA1, reducing the size of A11 cannot continue indefinitely, because at some point you will reach the smallest possible size and the process will have to stop. You cannot reduce it any below 0. And so the conclusion is that after finitely many steps, we would have cleared out all the entries in the first row except for the first 1/1 entry. So after finitely many steps, this process must stop, resulting in something like this: A11, 0, 0, 0, and whatever over here. Okay, now let's try to clear the first column. We can do exactly the same kind of thing to try to clear the first column, instead of column operations, we'll be doing row operations, and that process too must stop in finitely many steps. So we can try to get here 0, 0, 0, but not so fast. The problem is that in trying to get 0, 0, 0 here, we may have messed up these entries. These may have become non-zero. So now we are back to square one. The rows are now non-zero. The entries in the first row are now non-zero. But no matter, we again work with the rows and try to make them 0. In the process, well, we may turn the column entries non-zero. So what is the way out of this? The way out of this is the fact that each time we do this, we are further reducing D of A11. So this may in turn disturb the entries A12 to A1n, making them non-zero. But the point is, each time we have a non-zero entry in the first row or in the first column, we are able to do these row or column operations which strictly decrease the size of A11. So this process too must stop after finitely many steps. So then go back to, let's call this step something. Go back to reducing the entries of the first row to 0. This process again, since each time d of A11 decreases strictly, this process too must stop. This process, namely of trying to make the first row 0, then trying to make the first column 0, then trying to make the first row 0, and so on, must stop. Infinitely many steps. So we have succeeded, after finitely many steps, we would have succeeded in getting A to the form A11 0 0 0 0 0 0 and some matrix A prime. But we wanted that A11 divides A prime, all the entries of A prime. So if A11 divides all entries of A prime, then induction step is complete. Otherwise, there exists some entry A prime KL such that A11 does not divide A prime KL. So what we have is that somewhere in this mess we have this entry A prime KL, and we have all kinds of stuff over here, and this entry A prime KL is such that A11, it's not divisible by A11. So what you can do is, now you can just do, say, R1 goes to R1 plus RK. So what will happen is that will bring this entry A prime KL up here, and it will also mess up the rest of the first row. Okay, but then what you can do is you can again apply the Euclidean algorithm. So A prime KL is Q times A11 plus R, where D of R is strictly less than D of A11. So what you do is you do CL goes to CL minus QC1, and then you do C1 interchanged with CL. After you've done this, what will happen is that this R would have come here. Oops. And R would have come here, and of course we don't know what mess we have over here. We don't really care. The point is that this D of R is again strictly less than dA11. So it's like, the game is like this. We keep trying to achieve this induction step, this matrix A, this form D1 0 0 0 A prime, where D1 divides all the entries of A prime. But each time we try to do that, but each time we fail to do that, what we can do is we can do some steps to strictly reduce the size of D1, of the size of A11. And so after finitely many steps, we can no longer reduce the size of A11. So after repeating this whole process, so we are back to square one in some sense. Now we need to clear out the entries of the first row, then clear out the entries of the first column, which might disturb the first row, and so on. But this whole big process now we keep repeating, and after finitely many steps of this kind, we get a matrix of the form d1 a prime 0 0 0 0 0 0, where d1 divides all the entries of a prime. Now if d1 divides all the entries of a prime, and now you perform row and column operations on a prime, d1 will continue to divide all the entries of the transformed matrices, of the transformed matrix a prime. So when you now further take this a prime and apply this induction step to it, at the next stage you'll get d2, and then you'll get 0 0 0 here, 0 0 0 here, and you'll get a matrix a2. d1 will divide all the entries of this matrix d2 0 0 0 a2, and so d1 will divide d2, and then when you apply it to a2 you will get d3, and so on. So continuing in this manner, results in a Smith canonical form. Let us now address the uniqueness of the Smith canonical form. Suppose I have two matrices. The first is A, D1, D2, DR 0 0 0, and B is E1, E2, ES 0 0 0. And suppose I know that A is equivalent to B. Then I want to show that the ideal generated by DI is equal to the ideal generated by EI for I equals 1 to R, and R is actually equal to S. It's easier to just show that the ideal generated by D1 is equal to the ideal generated by E1. Why is that? So let's denote by parentheses A the ideal generated by all the entries of the matrix A. Now suppose we have that B is equal to GAH. Then what does that mean? That means that each entry of B is given by a sum of entries G I K, A K L, H L J. So where we will be summing over K and L over appropriate indices. So the entries of B are of this form, which means that certainly all the entries of B belong to the ideal generated by the entries of A, which implies that the ideal generated by the entries of B are contained in the ideal generated by the entries of A. Now if A and B are actually equivalent, then these matrices G and H are invertible. So then I can write, then we can take A as the form G prime B H prime for some matrices G prime and H prime, maybe the inverses of G and H if they were invertible, and so we get that the ideal generated by A would be contained in the ideal generated by B. Putting these together, we get that the ideal generated by the entries of A is equal to the ideal generated by the entries of B. Now let's go back and look at these two matrices in Smith canonical form. Clearly, the ideal generated by the entries of A is, well, the ideal generated by D1, D2, D3 and so on. And I forgot to mention, we have the additional condition that the ideal generated by D1 contains the ideal generated by D2 and so on, and the ideal generated by E1 contains the ideal generated by E2 and so on, which means that the ideal generated by the entries of A is D1 and the ideal generated by the entries of B is D2. So the ideal generated by A is D1, ideal generated by D1, and the ideal generated by B is the ideal generated by E1. So this implies that if A is equivalent to B, then the ideal generated by E1 is equal to the ideal generated by D1. So this proves part of the assertion of the uniqueness of Smith canonical form. How are we going to show that the ideal generated by D2 and E2 are the same, for example? So we will use the following lemma. The ideal generated by, so let A be a matrix of the form D1, D2, dr 0, 0, 0. So it's in a Smith canonical form. Then the ideal generated by k by k minus of A is the ideal generated by the product D1, D2, dk. Well, this is not at all difficult to prove. The point is that the only non-zero minors of this matrix are going to be the minors where you choose the same rows as you choose the columns, and in that case the determinant is just going to be the product of the diagonal entries in those rows and columns. So the all k by k minors of A are either 0 or of the form di1 dik, where I1 less than ik. And so since the ideal generated by D1 contains the ideal generated by D2 and so on, the largest of all these ideals is the ideal generated by this product is just going to be the one where you take the largest ideals. Okay, now with this in mind, we can show that if A is equivalent to B, then the ideal generated by k by k minors of A is equal to k by k minus of P. Let's use this notation A subscript round bracket subscript k to denote the ideal generated by k by k minus of A. Now recall from the lecture on tensor algebras and exterior algebras that wedge Ka has as entries the k by k minors of A. So this matrix corresponding to wedge k of A on the kth exterior power has as entries k by k minors of A. We did that for square matrices, for matrices over a field, but it works equally well over a ring. And so what we have is that AK is just the ideal generated by the entries of wedge Ka. So now if A is equivalent to B, then we have B is equal to GAH for some matrix G in GLM R and H in GLNR. And likewise, we saw that the exterior powers, they compose nicely. So wedge KB is wedge KG composed with wedge KA composed with wedge KH. And this implies that the ideal generated by the entries of wedge KB is contained in the ideal generated by the entries of wedge Ka. And by symmetry you get that these ideals are equal. Therefore AK, so you actually get the equality, and therefore AK is equal to wedge Ka, which is equal to wedge KB, which is Bk. So the ideal generated by K by K minors of A has to be equal to the ideal generated by K by K minors of B. And now let's go back and look at our matrices in Smith canonical form. The ideal generated by K minors of A is exactly D1, D2, dk. And so what we get is that if A, which is D1, dr, is equivalent to B, E1, ES, then D1 dr, the ideal generated with these guys, is equal to E1 ES. D1 dk is equal to the ideal generated by E1 EK for all k. And once you go beyond R, both these have to be 0. And so R is going to be equal to S. Already we see that. And so what this means is that firstly D1 is some unit times E1, D1 D2 is some other unit times E2, D1 D2 D3 is some other unit times E1 E2, some other unit times E1 E2 E3. And using these identities, you can also show that D1 is some unit times E1, D2 is some unit, maybe different from this, times E2, and so on. Inductively. So for example, what we have is D1 D2 is U2 E1 E2, but what we know is that E1 is U1 inverse D1, so U1 inverse D1 and now in a Euclidean domain you can cancel, so this means that D2 is some unit U2 U1 inverse E2, which means that the ideal generated by D2 is equal to the ideal generated by E2, and so on. So this proves the uniqueness of the Smith canonical form.